Hello, dear students. Well, we have already studied about the VBT, and you know that the VBT it's been so important. Why it has been important? Because we can understand the construction of the complex compound. Very next one, that is the magnetic character and the hybridization. The three important things that will be considered in VBT. But you know that some of the complexes which have actually different you can say magnetic property and all, so that's why the improved you can say theory will be used, that is called the CFT. I mean to say today we will study about the CFT, that is the crystal field theory, right? So basically, it has been developed by Bethe and John von Wick. All right, and in this particular theory, we have to basically study about the splitting of d orbitals. Number one, the splitting of d orbitals, and the next one that is very important, that is the magnetic property of the complex compound. We can understand the magnetic property in VBT as well, but in case of what CFT we can discuss more clarity, you can say, in CFT what it's a magnetic property basically. And the next one, that is the colors of complex compounds. These things we can study in CFT, that is the crystal field theory. All right. So the next thing, which is basically very important, that in CFT uh, it will be divided into two parts, for coordination number 6 and for coordination number 4, right? So first of all, we will discuss about the coordination number 6, right? So CFT, that is the crystal field theory, and we have to discuss this CFT for coordination number 6, right? And you know that the coordination number 6 is, that means the central metal ion, which is a basically d block element, and it has been surrounded by a number of, you can say, ligands, and the number of ligands are no doubt 6 ligands. So 4 are here and 2 ligands are at these sites. So this will be the construction, and you also say that the construction will be what, it's octahedral. You can just mention like this. All right, the central metal ion, which has been surrounded by the number of ligands, and no doubt the ligands is actually give the kind of, you can say, construction which is octahedral, right? Clear? Here in CFT, we have to see one thing, that is the central metal ion, and the central metal ion definitely consists what, d orbitals. You see that the central metal ion, whose d orbitals are actually placed here, okay, and you know that the d orbitals are dxy, dyz, dzx, dx square minus y square, and dz square, right? I'm just mentioning here these dx square minus y square and dz square. I just mention here these two orbitals, dx square minus y square, dz square, and rest of these three are dxy, dyz, dzx. All right. In previous lecture, I think you understand that what the kind of, you can say, orbital constructions these d orbitals has, right? Double type, right? You also understand the construction of these two orbitals as well. Okay, so basically in CFT or crystal field theory, what is actually going on here? You know that the central metal ion is there, which is placed inside, and number of ligands are there. So basically, this is the positively charged central metal ion, and these ligands are basically negatively charged or maybe neutrally charged. Neutrally charged means some kind of dipole is there, like you can say water. It's a dipole. So negative portion of that dipole is actually surrounded to what? The central metal ion. Clear? There is a kind of you can say electrostatic interaction between the central metal ion and the ligands. Okay, again I just repeat, the central metal ion, which has what? D orbitals. This central metal ion is surrounded by what? Number of ligands. You know that the coordination number 6, there are the 6 ligands, and these 6 ligands are, you can say, negatively charged or neutrally charged. That means there's some kind of neutral molecule is there, like water. So what is water? Water is a dipole. So whose actually negative part just towards where? The central metal ion. Basically, the central metal ion whose d orbitals are actually splits due to the electrostatic interaction, between what? Central metal ion and the ligands. That's why the d orbitals are actually split. How they split? Like this. They actually split into two energy levels. You see that the two energy levels are, it's T2G, and the upper one that is being called EG, like this. Okay, this is the very center for you, and where you can see the splitting is can be explained, right? So d orbitals of the central metal ion, right, split it into two energy level. That is the low energy level, that is called the T2G, and the upper energy level, that is called EG. So we can mention these orbitals like this: dxy, dyz, dzx, right? These three, and these are dx square minus y square, and of course this will be dz square. Clear? So d orbitals of central metal ion split it into two energy level: low energy level, that is called T2G, and the upper energy level, that is called EG. Correct? So here we can say this is the very center. If we can mention the gap here, if it is 0, then it will goes down. That means negative portion, it's nearby 0.4, not delta naught, or splitting gap, and this will be at the upper energy level. That means what? It's up to 0. That means what? It comes in positive. You see that this particular energy gap, it will be positive. Correct? It will be greater at 0.6, and it is what? Lesser, it's 0.6, right? So in coordination number 6, the splitting will be like this, where at the low energy level this particular gap has to be low, and this particular gap has to be what? Bigger. Clear? So this is the splitting of the d orbitals, and you know that these you can say splitting is going on. It is just because of the what the ligands which are actually located outer side of the complex. That means it gives the kind of you can say electrostatic force. Due to this particular force, the d orbitals is degenerated into what two energy level, that is the T2G and EG. All right. So let's compare that how this CFT actually comes in in different cases when we consider the weak ligand and the strong ligand, right? Okay, let's see. Well, uh, there are two cases. The first one, that is the strong field ligand. If the complex having strong ligand, right? We can just mention that thing here. And if the complex having what weak ligand, that means two different cases we are actually studying here. Let's see that how the splitting is going on in such cases. So first of all, we'll discuss about the strong field ligand, right? There is a spectrochemical series which gives the idea that which you can say ion or molecule is you can say strong one or the weak one, right? I just mention later on, but today we'll discuss about the CFT and of course the strong field ligand and the weak field ligand for coordination number what 6. Let's see. First of all, that in strong field ligand, if we have, then you have to mention what d orbitals of the central metal ion here. All right, and d is you can say d orbitals are 5 dxy divided by dzx dx square minus y square dz square, like this, and you see that this is the splitting gap. All right. For coordination number 6, I'm just mentioning here the 3 boxes or 3 orbitals. These 3 orbitals, they're actually located downwards, right? And these 2 orbitals are actually moves upside like this. It's T2G and this is EG. Clear? So it's a strong field ligand what splitting of d orbitals. Well, in case of weak field ligand, you can simply justify that where the kind of you can say weak ligand and the strong ligands are used. So just simply see that these are the d orbitals for you can take different case where the weak ligands are there, right? Okay, weak ligands like F negative, Cl negative, whatever, right? I just mentioned earlier, later on, and you see that the 3 orbitals are actually goes down here. They're just mentioning 3 orbitals, and of course 2 orbitals, these two. All right, it's T2G and EG. You see that there is the difference between the energy gap. This is the energy gap. You see that the T2G and EG, this energy gap is bigger and this energy gap is shorter. Okay, very important thing. If we have the weak field ligand, then the splitting gap must be what? Greater. This will be greater. All right. So always you remember this strong ligand if we have, right? If the complex having strong ligand, then always low spinning will be there. Low spinning. Clear? SLLS. If we have the weak ligand, then definitely high spinning will be there. So low spin complex and high spin complex, they are the two kinds of, you can say, cases we can discuss. All right. So what I am mentioning here, I'm just mentioning here the magnetic property of you can say each case. Let's see. Suppose uh, I have D4 orbitals in what central metal ion. D orbital consists 4 electrons, and here we have the d orbitals consist 4 electrons. So how can you fill, right? How can you fill? Like this: 1, 2, 3 and 4. Clear? And these 4, 1, 2, 3 and 4. Clear? If d orbitals consist 4 electrons, and the complex with that will be what the strong field ligand, it consists strong ligands, then how the electrons are actually goes inside these orbitals. Let's see. First of all, you have to mention this electron like this. Okay, it goes down actually. The next one, that is here. Okay, this electron moves this side. You see that this particular electron, right, it goes inside this box, opposite direction. Rotation will be opposite direction, right? So we see that the fourth electron, it doesn't have any kind, you can say it doesn't have the energy to bounce from this T to G to what EG. This electron, it doesn't have that energy which can bounce from T to G to what? EG. That is mean because the energy gap is greater. Alright. So energy gap is greater, that's why this electron goes into T to G. That means the pairing is there. So electron pairing is there. That's why it has been low spinning. Alright? Clear? Now, you see that in this case where the weak field ligand are there, then no doubt the gap will be narrow between the T2G and EG. So this electron is going in this box. This electron goes in the next one. This electron moves in the next one box. But what about the fourth one? This particular electron is going in this box, but you see that the gap is narrow. That's why this electron shift in the EG. So we can remove this electron, right? And it will be shifted in what? EG. This is the difference. So you see D4 condition is there. Here the unpaired electrons, this is pair 1, and unpaired electron value that comes 2 electrons. Here the unpaired electrons number, n number 1, 2, 3 and 4. Alright, clear? And you know that what is the formula? Formula is mu, that will be mu bm, that is it's a root n plus 2. Clear? So n equal to 2, that will be what? It's a root, it's 2 and 2 plus 2. Okay, that is 4 to the 8, that means root 8. It will be it's 2.8 nearby, so it will be paramagnetic, right? This is the formula, simple formula we can use already in VBT. And what about in n equal to 4? It will be what? It's basically mu. It's root 4 and 4 plus 2. It's 6 4 jet 24 root 24. It's 4.8 or nearby. So which is more paramagnetic? This one, because whose n value is 4. Clear? So this is the CFT for you, and here we have discussed the CFT for coordination number 6. All right, I hope so. You can understand that what is the CFT. All right. Well, you see that there is the spectrochemical series, and the spectrochemical series gives the idea that where the weak ligands and the strong ligands are there. So you see that I negative, Br negative, S2 negative, SCN negative, Cl negative, F negative. Basically, these are the weak ligands, right? OH negative, all right. C2O4 oxalate ions, all right. O negative 2 and H2O, and of course afterwards, that means these are the what? Strong ligands, right? Okay, you see that the weak ligands and the strong ligands, if we go left to right in this spectrochemical series, then what? uh, there is the increasement in the delta naught value, right? Okay, weak ligands and strong ligands. So we can go for this particular spectrochemical series. So it's a very important, you have to learn this series too. All right, now we'll discuss about the CFT for coordination number 4. Let's see that. Well, CFT for coordination number 4, and we know that the coordination number 4 means the central metal ion which is surrounded by 4 ligands like this. Okay, and these 4 ligands make the construction tetrahedral or square planar. This will be the square planar construction. This will be what it is, tetrahedral construction like this. Okay, coordination number 4, and we are discussing about the crystal field theory. Okay, well, we have the, you can say, tetrahedral construction. The tetrahedral construction is this: the central metal ion, ligands are here. Okay, example of this that is NiCO4, right? You see the central metal ion surrounded by 4 ligands, then no doubt the d orbitals of these central metal ion, which is mentioning here. Okay, similarly dxy divided dzx, dx square minus y square dz square, right? And the 4 ligands are there due to this particular reason. What is going on here? You see, it's the low energy level. At the low energy level, you see that these 2 boxes, right? These 2 boxes goes down. Yes, just reverse of what? Octahedral complexes for coordination number 6. We have already discussed, right? These two orbitals goes down, it means it's Eg, and you see these three orbitals moves upward like this. Okay, it's T2G. Okay, fine. I hope so clear. It's been clear to everyone. For coordination number 4, d orbitals of the central metal ion split it into two energy levels. The first one, that is the Eg, where you can say dx square minus y square dz square. Here we have the dx square dzx xy, sorry, dyz dzx, right? These orbitals moves away, or you can say upward. This is the barycenter for you, and this particular one is greater. Okay, so minus 0.6, this will be the value, and here you can say the gap, this will be, it's a barycenter 0, right? Where the splitting is actually going on, it will be 0.4 not. Okay, so this will be the CFT for coordination number 4 whenever we consider the tetrahedral construction. In case of NiCO4, we can go for this kind of, you can say, splitting of d orbitals. Alright, but in case of what square planar construction, it will be quite different. Alright, okay, so let's see that the kind of, you can say, construction of the square planar complex and how the splitting is going on. Let's see. Well, you see that it's been a different case. If we have the complex whose construction is square planar, then the d orbitals is actually split into this way, right? So these are the d orbitals of the central metal ion, right? And these orbitals splits into two energy level, that is the T2G and EG, right? 3 boxes goes down and 2 boxes goes upward, right? T2G and EG. But meanwhile, you can see the redistribution of the you can say degeneration of the d orbitals is taking place here. That means the two orbitals of these two d orbitals, dx square minus y square dz square, it's split it like this. So upward we have a dx square minus y square, and it's this next one that goes down, that is dz square. But in case of this particular level where the dxy divided dzx are concerned, the one box goes upward, right? That is dxy, and the two boxes goes down, that is dxz and dyz. So this kind of, you can say, splitting is actually taking place in the square planar construction. All right, so that is the end of the CFT here, and we'll discuss in the next lecture, that is very important, but how the complex give a particular color, right? DD transition and all. All right, okay, bye bye.